Um, Hello everyone, welcome to this webinar on holistic urban water analysis with 3DI, an integrated approach. First of all, let me start by introducing myself. My name is Jonas van Schrojenstein Lantman. I'm the product manager for Nelen Schuurmans Technologies. And I will be hosting this webinar, and the webinar will be containing of the following contents. First of all, I'm going to give a really brief introduction of 3DI. Then I'm going to discuss some use cases of 3DI in an urban context. And then we'll go into the holistic urban water analysis. So what does that mean? How do we apply it? And what are the added benefits for using 3DI in an holistic urban water analysis? So first of all, if you've seen previous webinars, you know that I'm always giving a really short introduction of 3DI. First of all, 3DI is hydrodynamic simulations, basically interactive and online. So we don't only compute how much water is going to flow somewhere, but also we are going to include the timing. This can be applied for flood risk management, urban planning and drainage design, and integrated water management. If after this webinar you're interested in a free trial, just go to our website 3diwatermanagement.com and you can request a free trial, which will give you the option of trying out 3DI for a month for free. If after that month you decide you don't want to do anything with it, it just expires, and that's it. If you would like to know more about the product itself, you can directly book a product demonstration and send in your requests. So first of all, the 3DI itself, well, the development of 3DI started in 2010 by Stelling Hydraulics, Deltaris, TU Delft, and Nelen Schuurmans. Wait, I have to slide the panel away from the webinar because I cannot see the full slides myself. It's currently being distributed and developed by Nelen and Schuurmans. So after initial development, Nelen Schuurmans took over and is currently the distributor and developer. What we are doing is we are building software with expertise in the water domain. So we have software developers, but we also have consultants that are actively doing projects in the water sector, and we also have a department fully focused on urban water analysis. And we use that expertise directly into our software and trying to make the best software possible for helping consultants, not only our consultants, but also the other consultants and the companies and the governments that are using 3DI. So the applicability of 3DI is quite broad. You can use it for pluvial flooding, so result of flooding as a result of heavy rainfall. We see that more and more happening worldwide, but 3DI can also be applied for fluvial flooding, for coastal and estuaries, for water system analysis, for calamity flood models, etc. But in this webinar, I will mostly focus on the urban context. So to introduce that a little bit, let me first introduce a couple of use cases. The first use case is about climate resilience on the Centrum Island in Amsterdam. This is a part of Amsterdam where they're looking into making it more greener and also making sure that what is being done has an impact also on the water management in that area. And what is nice about it is that, of course, you're not only looking at adding the green areas, for example, but you also want to include infiltration into the ground, the effect on the groundwater. As you can imagine, that groundwater might be an issue in Amsterdam. And take that whole aspects into account, not just having the heavy rainfall, but also taking into account the effects that it has on the groundwater level, and also potentially if there is open water that might be affected, take that into account. So then you take look at the not only at the water system, but basically as the built environment as a whole. A bigger kind of situation is in the municipality of Assen, which is situated in the northeast of the Netherlands, and it consists of an urban area surrounded by a large rural area. And what we see here is that there are some primary drainage channels and some secondary drainage channels, and it's all intertwined with the sewerage system in that area. So if, for example, you want to have a look at climate change scenarios, you want to see, okay, how much will, if we have heavier rainfall in the future, how will that affect the water system? Will people have problems with it? Will there be water on the streets, etc.? It is not sufficient to only look at the sewage system itself. You have to also look at the open water, the flow on the ground. You have to take the whole water system as a whole. You have to have a holistic approach to this water system. And that is a complex endeavor to do that for such a large system. But with 3DI, we have built a model that encapsulates basically the whole municipality in one, and also uses the digital elevation model and uses also the sewage system and the open water as well. So it's basically a very large 1D, 2D simulation where the water is flowing from the roofs into the sewer system, but also from the surface of the streets. It can also just have some runoff there and then go into the sewer system or not, depending on the local situation. And this gives the municipality insights, accurate insights in what is going to happen in the future, and gives them a chance to play with several scenarios and do the right investments for climate adaptation. So if we look at the applicability of 3DI in an urban context, well, I mostly want to talk about the holistic urban water analysis, but when I was making these sheets for this webinar, it felt that I first need to also point out two other type of analysis that is being done if you look at the urban water system, and show how you can do that with 3DI. Also, what is the impact of these scenarios, why you would want to do them or why you don't want to do them. There are, of course, always pros and cons for every kind of analysis. So this is a rough approach. There's, of course, a lot of in-betweens, but this is just to give you an idea of the applicability and the broad range of possibilities that you have with 3DI. So to introduce that, I'm going to point to use the three pillars. First of all, we are going to look at the computational core. What does the computational core bring into the to mix with a certain type of simulation? How are you able to use it using the modeler interface, and how are you being able to either see the simulations live or to interpret the results in a visual way? So well, let's say traditional urban analysis, you are mostly looking at a sewerage network computation. So you're only looking at the pipes, the manholes, you add some inflow parameters, you add, okay, I have so much inflow from a certain area, like for example, on a certain manhole, you have 3 roofs, they add up to, I don't know, 40 square meters, and you add that to the manhole just as a number. And that is nice because it is very easy to understand also what is happening in the system. You can easily compute what is happening there, and it's very suitable for dry weather flow design and analysis. You can, of course, do a proper analysis of the functioning of the sewage system. Are the pumps working as expected in this kind of situation? Is the weir overflow working as expected? And it really depends a bit on the location and design criteria that went into when you are building a sewage system. But in the Netherlands, for example, the design is usually around 20 millimeters of rain that it can handle. So if there is going to be a heavier rainfall analysis, a heavier rainfall than this 20 millimeters, what will happen is that there is going to happen a lot with the water above ground. You see that if you have a heavy rainfall event, then water is flowing on the streets. It's not necessarily even going to the sewage system anymore. And in this kind of situation, then this kind of simulation, this kind of analysis might not be the most accurate depiction of reality. Also, when you're looking at climate adaptive measures that you are taking nowadays, you're not just making the sewage system bigger, you're also looking at above the ground. You're looking, can I store water here? Can I make retention basin? Can I make ponds, for example? That is something that is very hard to incorporate in these kind of analysis. But it is still being used, of course, and of course you can do this with 3DI. And just as an example, I've taken a small part of a model, and I've run several simulations with different settings just to show the impact. So first of all, let's look at a traditional urban analysis, and I've put a aerial photograph on the background just to have an idea of where this is located. Of course, it doesn't do anything for the simulation. What we have in this simulation is a combined sewer flow, and also here on the side we have a separate rain stormwater system. We have inflow directly from the roofs and dry weather flow. So if you're looking at 3DI, and what it can help you with is if you look at the pipes, we have built the 1D component from the ground up. So it is not a existing model that we use. It's not like we took SWIM or, for example, no, we built our own 1D simulation engine, and we added several extra things on top of that. One of them is that we include nested Newton, which means that there is no Priceman slot required. So for those of you that might not be aware of this, this is a pipe, and here on top we see a very small thin layer. And the moment the pipe is full with water, then in reality, the water will just go up in the manholes, but not in the pipes, obviously. But to make this, to be able to solve this numerically, what we do is add a very thin layer of water. And of course, for one pipe, it doesn't matter that much. But if you do this for a whole sewage system, then add it up. All this water that you're being added doesn't help when it comes to the being strictly mass conservative. So it adds some, and it also makes your simulation a bit less accurate. So if you are using nested Newton, what it means is that you can work with closed pipes on the top. So if you have these pipes closed on the top, it means there's no water going up, and all the water that's basically being pushed through this pipe, it might affect, especially under higher pressure, the results of your simulations. The calculations are more accurate, and it also ensures smooth transitions from unpressurized to pressurized flow. And of course, if you have a traditional model, you want to have inflow in the system. So this is a picture of a street. You see that the water might be going on the street, might be going into the gutters. It also falls on the roofs, and it goes through the pipes into the sewer system. So for traditionally, for example, I just picked an example for the roofs here. If it falls on a roof, then in reality, it will go through these pipes. It will go into into the sewer system. But what happens in the background is there's a very simple rainfall runoff kind of small model that takes the precipitation. You have some parameters for evapotranspiration, storage, infiltration, and runoff, and that will result in being the flow into the sewer system. This will this is of course this takes all this in short, but this is very traditional. This is basically how all these kind of simulations work. Of course, for dry weather flow, now you can connect every object. You can have complete freedom in what kind of dry weather flow patterns you want to add. You can have weekdays, you can have weekend days, and you can just adjust this flow. You can use maximum inward equivalence, inhabitants equivalence, but you can also use different kinds of parameters for that if you are interested in this kind of analysis. Of course, if there is a really heavy rainfall event, then this is just a small fraction of the heavy rain. So if you're going to analyze these results, and in this map you can see here the roofs are being connected to the sewer system, and you can have these longitudinal profiles where you see this water going on the streets, and you can also see the here in the red is where the water is going above the drain level, above the exchange level of the manhole. But the point is that the water is going up from the manhole and being stored there until there is space in the sewer system, then it's going down in the manhole. There's no interaction on the streets itself in these kind of simulations. And of course, you are adding a certain type of storage on these manholes on top of the ground, but this is usually being done as a kind of a standard approach. For example, 100 square meters, and that's it. So when a couple of years ago, maybe 10 years already, maybe more even, all worldwide there were more and more high resolution digital elevation models available. So for example, you can also do a study using only digital elevation models. And there's an example here. Of course, for reference, the sewer system is included. And basically what you do is you can do a quick scan. You can do urban analysis without the sewage network. So you're only simply looking at the overland flow to mimic the sewage system capacity, and the storage capacity is being deducted from the amount of rainfall. And this is perfectly fine if you want to test isolated cloudburst events with a rainfall amount that exceeds the storage capacity of the sewer system. But the moment there is kind of a different kind of rainfall, there's not just one cloudburst, but there's several cloudbursts, then of course the drainage capacity of the sewer system has to be taken into account. And what we can see is that maximum water depths can vary from real world events due to the fact that the sewage system takes care of the drainage of the street. And it's very hard to mimic this behavior in an overland flow model. So how do we do this overland flow? This 2D simulation is that we do this flow on 2D using the subgrid methodology. And what this means is that we are looking at for example, on the left we see a computational cell. This is in 3D. So these brown are the pixels. But what we say is that for every computational cell, we can see one water level. So there's one water level for this cell, and for every cell we store the volume water level relationship. This has the added benefit that we are taking into account the high resolution digital elevation model when we are doing simulations, but we are computing on a coarser level. Does it matter? Yes, it does. If we are looking at the subgrid here on the left-hand side, for example, a cross-sectional profile of a channel makes it more clear, then we can see here that we have a kind of cross-section here, and here without subgrid you have to do something within your computational cell, and you don't want to compute on a pixel level because that will be computational very intensive. But what you can do is you can make the computational cells just as big as we do with here on the left hand side, but then you have to do some sort of averaging, for example, with the digital elevation model that is below it, and then you get this kind of wet perimeter, which looks completely different than what it is in reality. And if we look at a simulation example on the left hand side with subgrid, on the right hand side without subgrid, where we have a depth average per cell, then we can see that taking into account that the number of cells is the same and that the computational speed is the same, that the result is still completely different. And the same goes, of course, in the urban context. You have if you are looking at water on the streets and you're going to take the average digital elevation model in the streets, you might have the effect that that water is standing against the house, but in reality it is still in the streets itself, and it might completely affect which houses you are deemed to be vulnerable and which are not. So if we look at the results in the 2D, for example, on this model, we can see here, this is in the red circle, we can see here that the water is accumulating here. And of course, you can use infiltration rasters and say, okay, I want to use an infiltration raster here, and then try to mimic behavior of the sewage system, but it's very hard to make that to do that in a proper way. And if we are going to come back to this picture if we are looking at the holistic urban water analysis. And what we mean by that is that we are going to include all the aspects of the urban water system. And it really depends on the area what you want to include. So if you want to include sewage flow, a digital elevation model, inflow from the houses, open water, groundwater. But you want to look at the water system, urban water system as a whole, and it doesn't end at the weir, it doesn't end at the overflow where the water is going out of the sewer system. No, that water is going somewhere, and you have to take into account where that water is going as well. If the overflow is going into a really small channel, then it might have an impact on that channel, a relatively higher impact than it will have if you are, for example, overflowing on a large river. So these kind of models, they are suitable for all types of rainfall events, so from cloudbursts to multiple rainfall events. And it's important to note that although this is the kind of the best kind of simulation that you can do, you have the most accurate simulation of what is happening in the real world, but this is also the most complex type of model to build. You have to bring several kind of data sets together. You have to have a proper digital elevation model, and then you also need a connected sewage system. And if you look at this data for the sewage system, then if you have to prepare it for traditional urban analysis, you already have to do kind of certain kind of data mangling. But if you are going to add a digital elevation model to it, it adds another complexity. So as I said, sewage systems are almost always connected with surface water systems, so you have to take that into account. And climate adaptive measures, they are mostly taken above the ground, and this means that it needs to be included in a modeling process. And with holistic urban water analysis, where the water is flowing on the streets, where the water is flowing overland, you are taking that into account. And this gives you the possibility to efficiently model climate adaptive scenarios, including all possible sustainable urban drainage systems that you can think of to mitigate climate impacts. So to do so, you have kind of different kinds of modeling concept. You can either use the 0D, the 2D, or the 1D. It doesn't really, it is up to the modeler, for the modelers in the room, to you, it's up to you to decide which kind of concept you are going to use. I've heard people modeling streets in 1D. Yeah, well, there is no right or wrong, but I would myself prefer it just simply as an overland flow kind of simulation. And also the channels, you can either use a digital elevation model including bathymetry, or you can use a cross-sectional profile in the channels that you get in the data directly from, for example, the government that is managing this area. So what does that look like? So the inflow can still come from the roofs. I already showed that, so I'm going to quickly to the next one. You also have the inflow from the streets. And if you look at other hydrodynamic simulation software, there are several ways of doing that. They can use the same approach as they do for the inflow from the roofs and say, okay, you have the streets, there's a certain area, and the water flows on it, and the water comes in, etc. But what will happen in reality is the water might be flowing on the streets, might not even go in the sewer system, and only when it connects to the gutters, to this kind of the drain level, the exchange level that you have, it is going into the sewer system if there is space available in that sewer system, or the water can go up from the sewer system and start flowing on the streets. And this is kind of like a complex behavior that you cannot really predict on beforehand. So how does that work? On the right hand side we see a profile of what that looks like. You have here a manhole surface level. That is basically this kind of the surface level of this one. The exchange level here is the exchange level of the gutter, and the manhole drain level is up to the user to set. If you set it below the lowest pixel that is available, then it will take the lowest pixel in the area. But if you set it higher than the lowest pixel, then it will just take that level, that value. And if we look at, we are talking about water that's flowing from 2D to 1D and 1D to 2D and all these kind of exchanges. And it is important to note that what we are doing here in 3DI is that we take integrated coupling by default. So for traditional software, is that there's something depends a bit on what papers you read or how they call it, but it's usually called something like along the lines of dynamic coupling. And what is happening there is that you have a 2D surface flow model where the water is flowing on the streets. You have a 1D pipe model where the water is flowing through the pipes and they're being connected. And then you have to somehow figure out how to exchange the water between these two models. So if the water is only flowing through the pipes and there's only flowing water on the surface, it's relatively easy, it can be relatively fast. But the moment you start exchanging these kind of this water between these two models, then you have to figure out how much water is going to be exchanged between these models. And this happens within the software itself. As a user, you might not even know much about this, but what you say, for example, is I want to have I accept a certain kind of accuracy. But I want a speedy model. So then it says, okay, you want a speedy model. I want to have it fast. Then I'm going to swap large amounts of water. I'm just going to guess roughly how much water is going up and how much water is going down, and that's it. And that contributes to the mass balance error in your simulation. So if you do this kind of simulation, I encourage you to look at the flow summary. Every kind of software has a flow summary, and look how much water, what is the volume of error that is estimated in this flow summary, and then see how comfortable you are with that. What we do with 3DI is different. We are not doing this dynamic coupling. What we are doing is integrated coupling. So we have a surface flow and we have 1D pipe flow, and these are all computed at the same time. This is the same model. There is no difference. When you have our computational core, the sewage model and the sewage simulations and the surface flow simulations are being computed together. Just as an example, I mean, the same goes for the groundwater. That is also being incorporated in this as well, but then the figure gets a bit more complex. Because we are computing everything at the same time, this means that it's also more accurate. The mass balance error, if you are looking at it in the flow summary, can be along the lines of milliliters. This can be a very small area, very small volume, I mean. And that's nice if you are looking into accuracy, if you want to make sure that you are not having too much estimates in your simulation. And because we have these kind of interaction, it also means that it's faster than a traditional technique. And also, as I understand it from people that are coming from other kinds of software packages, it is also more stable than the dynamic coupling. This is, I think, what I should be saying about this. So if you remember the results that we had from the 2D kind of simulation, and we now added the sewage system, you can see here that, for example, for this particular case, the maximum water depth on this area is way lower. This is also, of course, a simulation, if I recall correctly, that was 2 times 20 millimeters in an hour. So it was more than enough to reach the capacity of the sewer system. but also the drainage of the sewage system will take will play its part in the second or the third hour of the simulation when the water is being drained. And you can see the result here. There is no water on the street, or not as significant as it was in the 2D part. So that gives you a better insight in the in what might be happen in case of a heavy rainfall event. The reason I'm pointing it out is that sometimes people say, okay, I'm going to do a 2D simulation, just overland flow, and I'm going to have insights in where I might have water accumulating on the streets, and I'll have a first rough insights. That's absolutely correct. But what what's sometimes being neglected is that the result might differ the moment you include the sewer system, and that you should not use that kind of analysis if you are going to do large investments in your sewer system. If you're going to do large investments, you're going to build something in the urban area to mitigate the climate change, to mitigate how the water is going to flow. Then you want to have also a simulation where you are certain that what you are going to build is going to give the right results, and that you're not trying to solve an area with large amounts of water which has no issue whatsoever. So that's really like from the computational core perspective. So the added value of using 3DI for these kind of simulations. But of course, this is nice if you have a computational core, and that's how we started. Of course, we started with the computational core. We want to have a very nice fast computational core that can rely on, but then you also want to be able to use it. And that is, of course, for engineers very important. And that's why we built the modeler interface, which makes it easy to use for modelers. It is incorporated in QGIS. QGIS is, for those of you that don't know it, it's open source GIS. It is the largest open source GIS package in the world. And the moment you are going to build any schematization in any kind of software, you are sort of doing GIS work. And when we were building schematizations in the past, we were using GIS, and then we were converting it into a third-party hydrodynamic software. But then you always have to do some sort of conversion. And then we decided when we were building 3DI, isn't it nice if your GIS representation is basically your schematization? And that's what we have done here. So the schematization is a simple database, vector database with raster datasets that you can edit in the modeler interface. If you have a different GIS software of choice that you want to use, you can use it for editing as well. But you will not have the tools to your availability that we supply here in the modeler interface. So we have, for example, made some editing tools. If you, for example, need to add a sewage pipe, you for the software, you need a manhole and a connection node, and you need to put everything in place. So we have built editing software. If you add a pipe, then all these kinds of required features are being added automatically, and they're being filled with default data that makes sense. So in this example, a pipe is being added from here to here, and for the manhole here, the same data, the same bottom level, drain level, exchange level is being used as this one. It's just being copied. And this makes sensible defaults, but of course you have to check it when you are editing to make sure that these are the right values. And the invert levels of the pipes are also being filled in automatically. But well, by default it will be flat, and most likely you will want to have an incline in your sewer system. But it already helps you quickly to add your pipe. This is basically what you need to add a pipe. Of course, there's something called snapping. So the moment you want to add the pipe to a certain manhole, then you have snapping to use as well. So not only that, you can use different kind of styling tools. For example, you can style the pipes in a certain way, but you can also do the same. There are all sorts of presets for styling, not just for the pipes, they're also for the results. And it might be that you are in need of, for those of you that already use 3DI, that you are in need of a certain kind of result styling. You don't know how to make it, please ask us, let us know, and we'll be happy to assist you, and perhaps also add it to the default styling that is available in your toolkit for 3DI. Recently, we have added several things to help you quick start your model. So, for example, add data from a open source, from a open data portal, and here there's a WFS. You copy paste them basically from the WFS into the schematization of 3DI. You have to tweak a little bit of things, and basically after you have done that, you can run a tool that connects the buildings, in this case, to the manholes, and there you have it. You have a connected buildings to the sewer system. When I was starting in this as a junior consultant, I built this kind of tooling myself 15 years ago. I can tell you it was not as fast and quick as with what we are seeing here. I'm very happy with this adjustment, this addendum. Of course, the moment you are going to use anything with a digital elevation model, you need to generate a computational grid. This can be quite labor intensive if you have to do this all from scratch, but with 3DI you can just generate a computational grid based on your preference. So in this case, there is a polygon that says, I want to refine here, and then here you see automatically that it is being refined here and it's coarser outside the computational grid. We have recently added a vector data importer, which is a very, very difficult name to say. You can just take source data from a shapefile, for example. You can load it in and you can connect to it, and you can say, okay, this attribute in the shapefile, that's friction type, this is sewage type, and then convert it. And this works with templates as well. So if you have always the data in the same data set, you can save the template and you can load the template next time you need it, and you're there. You have your first setup for a software, for a model. So the model interface is how you work locally. The moment you need to do a simulation, you upload it to the cloud. This automatically gives you management and versioning. So every version that you upload is a version, and also makes it able to work together with your peers, to work together on the same model, but also gives insights, for example, to customers, to clients. If you're working on their system, they can also see, okay, in this schematization, the weirs have these and these levels, and that also minimizes the need for exchanging, for example, Excel sheets with values of weir levels, for example. And of course, you can do online, live, and interactive simulations. What is good to know is that when you're using the model interface, this is a local installation, and these schematizations are all local. So the moment you stay local, you don't need a license. And the moment you have done a simulation, you have run the results, you can also download the results, and you don't need a license the moment you are going to do offline analyzing. You can do it also in the train or without any internet connection available. But it also means if you have, for example, you want to show it to a colleague or you want to show it to a client who has to be technical enough, of course, to be able to understand this, you can just send the whole package. You can send the results. You can send the installation for the model interface, and they can just check it out themselves if they want to. So, of course, if you do these kind of simulations, we have talked about the holistic approach, where you are looking at how in terms of where the water is coming from, where the water is falling. But it is not only about building a right schematization. It's also about how much water is actually going into this simulation, and is that accurate enough? Is that you also want to use the best data available there? And that's why we said, okay, you don't want to have only traditional time series of rainfall events, but also you want to include historic rainfall from rainfall radars, or for example forecasting data sets, because the rain, as you can see here, it is not the same everywhere. So the larger the area, the more different the rainfall impact might have. I mean, I was cycling yesterday, and I was 20 kilometers away from home. I got there, it was raining very heavily, but when I was home, there was almost no rainfall there at all. So basically, I should have stayed at home, and it would have been fine. But if you are looking at these kind of simulations, then the water input is might be just as important, especially if you want to show to people what happened in the past and you want to validate your simulation. So it's good to know that because we use a simple database, you can also use SQL for mass editing. It's not a prerequisite. You don't need to know what I'm saying now at all, but if you know something about SQL, you can use it, and it's very nice to do mass editing that way. If you make any mistakes, it doesn't matter. I mean, you have uploaded a previous version, if all is well, to the model data bank, so you can just download it and go back to a previous version if you made any mistakes. You can also build your own plugins. QGIS and the model interface allow you to do so. You can share those with others. You don't have to share them with others, but basically every plugin that you build is Python and open source by default, because it is in an open source package. And you can also use all the processing tools from QGIS to your advantage. If you want to see examples of plugins, then I forgot to include the URL, but I can add it to the notes. Is you go to github.com/3di. You have to completely spell it in letters, and then you can find all the tools and plugins that are freely available for everyone. So I already mentioned the management and the versioning. If you are going to look online, you can see, if you have a large area, where there are all sorts of different kind of models available. And we have done our recent customer survey, and what we are seeing is that people were very happy with how it was working, and they found it very easy to build schematizations. So just very shortly, I'm reaching the end of the webinar. What we have also, it's also possible to, of course, show visually to your customers, to your clients, how the water is flowing. For that, we have added 2D flow on the surface, so that gives some extra insights as well. You can also communicate the results if you have the possibility, if you have the 3DI scenario archive, to use the 3DI scenario archive to make, for example, animations of past simulations that you've done. And you can also add points of interest and do a short analysis of those points of interest using the graph tool here. You can also use the automated post-processing. So, for example, different water depths over time, flood hazard rating, rainfall that went into it, especially useful if you used, for example, a radar rain. Also, the rate of rise might be useful in case of flooding. Well, this kind of automated post-processing is included. And what we have recently included, which is not in the screenshot, is the vulnerable buildings, which you can also use to compute from the max water depth of a scenario, which buildings are more vulnerable than others for this scenario. You can do all sorts of visual in the map view. I'm going to go over this due to the time, but I want to point out this one is that you can use the watershed tool to have insights in where the water comes from, and especially also where the water is going to. But of course, it's nice to see that, oh, if I click here, oh, the water is coming from this whole area. That's of course nice. But you can then also draw some lines and compute how much water is actually going over that lines, and to see okay, this is like, I don't know, for example, here it's 1200 cubic meter. So if I don't want all this water to go here and accumulate here, then I have to figure out how to store this volume of water for this kind of scenario here more closer to the source. So that is kind of a nice way of visualization. You can also do a water balance per area and make a flow pattern. And of course, this is what I just mentioned. Post-process to impact. So clients might not just be interested in the water depths. That's of course always nice to see the water depth in a certain scenario, but they also want to know, okay, which buildings are being vulnerable, are very vulnerable, or potentially vulnerable. That is also a very a nice add-on to what you can do. And of course, you can also use third-party 3D software for visualizations. So for example, if you have a 3D digital twin available, you can also include for this kind of result into your 3D digital twin for communication purposes. The latest developments coming shortly is the water quality, where you can assign water a label, and it's based on the location, for example, whether rainfall occurs, or the inflow type, for example, dry weather flow, and then you can track the water across all the domains. So you can see whether the sewage water is going into the surface water, how much that is, and how it actually goes into this kind of system. And if you have included groundwater, you can also see how the water is going, how this kind of substance is also going through the groundwater. You see here on the right-hand side, really in shortly, a real-world river that sort of like has a inflow, but you can also use this for urban areas as well. And the vulnerable buildings I just mentioned. So that's really the whole package in short. So what we're talking about with 3DI is the holistic approach. I'm going to give you first a short characteristics of 3DI. We do the full symphony equations. We are computing all the water volumes and timings correctly. We can compute large areas using high resolution with subgrid. We can follow every drop of water above and underground. The model building is fully GIS based. We are a cloud-based hydrodynamic modeling software. You can interact with 3DI simulation in the browser and the live site. I've not shown it in full in this webinar, but other webinars or movies that you can find on our YouTube channel that will show you more in detail what I mean with that. And you can also fully control and interact your 3DI simulation using the Open API. You can do anything with it. So that means you can also just automate or script every step in the modeling process. And what we see is if you enable people to do that, they will also do that. So that's really nice to see. So why choose 3DI? Why choose 3DI in an urban context? Because you want to have the most fast and accurate computations. You want to make sure that the investments that you're doing in the urban area for the climate adaptation, for the mitigating measures, are the right investments. We're making it easy to use for engineers. That makes them being able to work fast and also to diminish any mistakes they might have that might clutter up the process or make the wrong decisions. And of course, thanks to the visual results and also the possibility to add 3DI live simulations and show to your stakeholders what is happening, it gives you a shared understanding of the water system, it gives you a shared understanding of the climate adaptive measures that you have to take into the future.